Key formats. Both private and public keys can be represented in a number of different formats. These representations all encode the same number, even though they look different. These formats are primarily used to make it easy for people to read and transcribe keys without introducing errors. Private key formats. The private key can be represented in a number of different formats, all of which correspond to the same 256-bit number. The table below shows 3 common formats used to represent private keys. Different formats are used in different circumstances. Hexadecimal and raw binary formats are used internally in software and rarely shown to users. The WIF is used for import-export of keys between wallets and often used in QR code representations of private keys. Type raw, prefix none, 32 bytes. Type hex, prefix none, 64 hexadecimal digits. Type WIF, prefix 5. Description: base 58 check encoding, base 58 with version prefix of 0x80 and 4-byte checksum. Type WIF compressed, prefix K or L. Description: as above, with added suffix 0x01 before encoding. All of these representations are different ways of showing the same number, the same private key. They look different, but any one format can easily be converted to any other format. Decode from base 58 check. The Bitcoin Explorer commands make it easy to write shell scripts and command line pipes that manipulate Bitcoin keys, addresses, and transactions. You can use Bitcoin Explorer to decode the base 58 check format on the command line. We use the base 58 check-decode command to decode the uncompressed key. $BX base 58 check-decode 5J3M ... The result contains the key as payload, the WIF version prefix 128, and a checksum. If we apply the same command to the compressed key, the payload will have an additional suffix 01, signaling that the derived public key is to be compressed. Encode from hex to base 58 check. To encode into base 58 check, we use the base 58 check-encode command from the Bitcoin Explorer and provide the hex private key, followed by the WIF version prefix 128. $BX base 58 check-encode 1E99 ... version 128. Encode from hex to base 58 check. To encode into base 58 check as a compressed private key, we append the suffix 01 to the hex key and then encode as in the previous section. $BX base 58 check-encode 1E99 ... 01 ... version 128. The resulting WIF compressed format starts with a K. This denotes that the private key within has a suffix of 01 and will be used to produce compressed public keys only. Public key formats. Public keys are also presented in different ways, usually as either compressed or uncompressed public keys. As we saw previously, the public key is a point on the elliptic curve consisting of a pair of coordinates, x, y. It is usually presented with the prefix 04, followed by two 256-bit numbers, one for the x-coordinates of the point, the other for the y-coordinate. The prefix 04 is used to distinguish uncompressed public keys from compressed public keys that begin with a 02 or a 03. Here's the public key generated by the private key we created earlier, shown as the coordinates x and y. X equals F02 ... for 1A. y equals 07c ... BDB. Here's the same public key shown as a 520-bit number, with the prefix 04 followed by the x and then the y coordinates. Big K equals 04F02 ... 41A 07C ... BDB. Compressed public keys. Compressed public keys were introduced to Bitcoin to reduce the size of transactions and conserve disk space on nodes that store the Bitcoin blockchain database. Most transactions include a public key, which is required to validate the owner's credentials and spend the Bitcoin. Each public key requires 520 bits, which then multiplied by several hundred transactions per block or tens of thousands of transactions per day adds a significant amount of data to the blockchain. As we saw in a previous section, a public key is a point x, y on an elliptic curve. Because the curve expresses a mathematical function, a point on the curve represents a solution to the equation, and therefore, if we know the x-coordinates, we can calculate the y-coordinates by solving the equation y squared equals x cubed plus 7 modulo p. That allows us to store only the x-coordinates of the public key point, omitting the y-coordinates and reducing the size of the key and the space required to store it by 256 bits. An almost 50% reduction in size in every transaction adds up to a lot of data saved over time. Whereas uncompressed public keys have a prefix of 04, compressed public keys start with either a 02 or a 03 prefix. Let's look at why there are two possible prefixes. Because the left side of the equation is y squared, the solution for y is the square root, which can have a positive or negative value. Visually, this means that the resulting y-coordinates can be above or below the x-axis. From looking at the graph of the elliptic curve, the curve is symmetric, meaning it is reflected like a mirror by the x-axis. So, while we can omit the y-coordinates, we have to store the sign of y. Or in other words, we have to remember if it was above or below the x-axis, because each of those options represents a different point and a different public key. When calculating the elliptic curve in binary arithmetic on the finite field of prime order p, the y-coordinate is either even or odd, which corresponds to the positive/negative sign as explained earlier. Therefore, to distinguish between the two possible values of y, we store a compressed public key with the prefix 02 if the y is even, and 03 if it is odd, allowing the software to correctly deduce the y-coordinates from the x-coordinates and uncompress the public key to the full coordinates of the point. Here's the same public key generated previously, shown as a compressed public key stored in 264 bits, with the prefix 03 indicating that the y-coordinate is odd. Big K equals 03 F02 ... 41A. This compressed public key corresponds to the same private key, meaning it is generated from the same private key. However, it looks different from the uncompressed public key. More importantly, if we convert this compressed public key to a Bitcoin address using the double hash function, RIPEMD160 of SHA-256 of Big K, it will produce a different Bitcoin address. This can be confusing because it means that a single private key can produce a public key expressed in two different formats, compressed and uncompressed, that produce two different Bitcoin addresses. However, the private key is identical for both Bitcoin addresses. Compressed public keys are gradually becoming the default across Bitcoin clients, which is having a significant impact on reducing the size of transactions and therefore the blockchain. However, not all clients support compressed public keys yet. Newer clients that support compressed public keys have to account for transactions from older clients that do not support compressed public keys. This is especially important when a wallet application is importing private keys from another Bitcoin wallet applications, because the new wallet needs to scan the blockchain to find transactions corresponding to these imported keys. Which Bitcoin addresses should the Bitcoin wallet scan for? The Bitcoin addresses produced by uncompressed public keys, or the Bitcoin addresses produced by compressed public keys? Both are valid Bitcoin addresses and can be signed for by the private key, but they are different addresses. To resolve this issue, when private keys are exported from a wallet, the WIF that is used to represent them is implemented differently in newer Bitcoin wallets to indicate that these private keys have been used to produce compressed public keys and therefore compressed Bitcoin addresses. This allows the importing wallet to distinguish between private keys originating from older or newer wallets and search the blockchain for transactions with Bitcoin addresses corresponding to the uncompressed or the compressed public keys respectively. Let's look at how this works in more detail in the next section. Compressed private keys. Ironically, the term compressed private key is a misnomer because when a private key is exported as WIF compressed, it is actually 1 byte longer than an uncompressed private key. This is because the private key has an added 1 byte suffix, shown as 01 in hex, which signifies that the private key is from a newer wallet and should only be used to produce compressed public keys. Private keys are not themselves compressed and cannot be compressed. The term compressed private key really means private key from which only compressed public keys should be derived, whereas uncompressed private key really means private key from which only uncompressed public keys should be derived. You should only refer to the export format as WIF compressed or WIF and not refer to the private key itself as compressed to avoid further confusion. Table 4. Example, same key, different formats. Hex format, private key, 1E99 ... AEDD. Hex compressed format, 1E99 ... AEDD01. WIF format, 5J3M ... 1JCN. WIF compressed format, KXFC ... VRTJ. Notice that the hex compressed private key format has 1 extra byte at the end, 01 in hex. While the base 58 check version prefix is the same, 0x80, for both WIF and WIF compressed formats. The addition of 1 byte on the end of the number causes the first character of the base 58 encoding to change from a 5 to either a K or L. Think of this as the base 58 equivalent of the decimal encoding difference between the number 100 and the number 99. While 100 is 1 digit longer than 99, it also has a prefix of 1 instead of a prefix of 9. As the length changes, it affects the prefix. In base 58, the prefix 5 changes to a big K or big L as the length of the number increases by 1 byte. Remember, these formats are not used interchangeably. In a newer wallet that implements compressed public keys, the private keys will only ever be exported as WIF compressed with a big K or big L prefix. If the wallet is an older implementation and does not use compressed public keys, the private keys will only ever be exported as WIF with a 5 prefix. The goal here is to signal to the wallet importing these private keys whether it must search the blockchain for compressed or uncompressed public keys and addresses. If a Bitcoin wallet is able to implement compressed public keys, it will use those in all transactions. The private keys in the wallet will be used to derive the public key points on the curve, which will be compressed. The compressed public keys will be used to produce Bitcoin addresses, and those will be used in transactions. When exporting private keys from a new wallet that implements compressed public keys, the WIF is modified with the addition of a 1 byte suffix 01 to the private key. The resulting base 58 check encoded private key is called a compressed WIF and starts with the letter big K or big L, instead of starting with 5, as is the case with WIF encoded keys from older wallets. Tip: compressed private keys is a misnomer. They are not compressed. Rather, WIF compressed signifies that the keys should only be used to derive compressed public keys and their corresponding Bitcoin addresses. Ironically, a WIF compressed encoded private key is 1 byte longer because it has the added 01 suffix to distinguish it from an uncompressed one.